Ladies and gentlemen, at exactly 4 p.m. on Tuesday, November 2nd, it is time for a brand new Epic product launch. And as usual, we have selected Epic members who each have an important development to announce to the rest of the world. In this edition, those companies are Instrument Systems, Dynamic Optics, LightTrans, Lidaris, MPS Micro Systems, and Emberion. Let's open up the Zoom room and get started. Ladies and gentlemen, welcome to another Epic Members new product release today on the 2nd of November. As usual, we have selected key companies in the sector that have something big to announce to the entire Photonics community. It is a big day because we really today to have something very, very, very special. It is really how we brought Emberion, Lidaris, Dynamic Optics, Instrument Systems, LightTrans, and MPS Micro Systems. We do have 6 fantastic products, but every product needs a system integrator. So this is a call for all the system integrators in the Epic community. Try to understand how this product can make a difference in your system. Today, we're going to have the presentation from Instrument Systems talking about their camera from pixel testing, near field measurements on pixel technology. Dynamic Optics, going to talk about the adaptive optics and the deformable mirrors. LightTrans has something big to announce, the new tool for ray and physical optics modeling. Lidaris is going to tell us how they can do CW measurement of a laser-induced damage threshold. MPS Micro Systems, they're going to talk about the linear lens actuator. And last but definitely not least, all the way from Finland, we're going to have Emberion talking to us about their new shortwave infrared and visible camera for their new own sensor technology. So let's start the meeting. Let's go all the way to Munich. And we go all the way to Munich to talk to the company Instrument Systems. They have a new product, a very important product for the testing of pixels at large volume. We are talking about measuring the near field of the pixel with a brand new testing camera BTC 4000. And for doing that, nothing less than the program manager for pixel testing, Karthik Iyer. Karthik, thank you very much for being with us. The floor and the attention of everyone goes to you.
Thank you, Jose, and good afternoon, everyone. I hope everybody can see me and hear me. So thank you for the entire Epic team as well to give us the opportunity to present this unique product in the field of pixel testing and metrology to the esteemed Photonics community that is present here today. So let me start by giving you a brief introduction about who we are. Instrument Systems was founded about 35 years ago in '86 and is part of the Konica Minolta group since the last 7 years. We provide testing and measurement solutions for a wide range of industries, including display manufacturing, infrared pixel manufacturing, and automotive sector. We're based out of Munich and with a branch in Berlin as well, where at these sites we develop and manufacture our entire product line. Apart from that sites, we have a network of distributors and calibration labs across the entire globe. From the wide range of application areas that we cater to, like display measurement and LED measurement technique, today I will be presenting you or focusing on our products in the pixel testing and metrology field, especially the BTC 4000, the near field pixel testing camera. Just to start it, let me give you a quick overview of the pixel technology portfolio that we offer. We provide testing solutions for the comprehensive characterization and inspection of the temporal, spectral, electrical, and spatial properties of pixel. So you combine a high-resolution spectrometer with an integrating sphere and a photodiode, you get a fast, reliable, precise test equipment. You include the PVT, the pulsed pixel tester, which extends the photodiode and spectrometer configuration with a nanosecond pulse driver electronics and fast photodiode. Then it completes the package of a complete electrical, spectral, and temporal characterization. And adding to that, the camera-based systems that will then give you the solution for your spatial characterization. The good thing about all of these products is that these products can not only be used in the laboratories, but also in the production lines at the different stages of the VCSEL value chain, especially to meet those challenges associated with testing and characterization in those at those stages, especially at the wafer level. It has been known that it's a challenge, and we are ready to meet those challenges with the VTC. To just give you an idea, how does this translate into a real world application? Like of a VCSEL, if I take an example of a time of flight, you can see that we have the products that cater to all of the properties that are needed to be measured. For example, let it be the pulse, the diffusion for the beam profiling, or even at the single emitter level, which is the near field camera, the VCSEL testing camera 4000, which I will be presenting to you from now today. So, as we are aware, identifying the functionality and quality of VCSEL's array on the single emitter level is a very important task, especially in the production environments, and can be carried out this can be carried out by the VTC 4000. This is a specially designed system, consists of a camera and microscope optics, and permits measuring the spatial distribution of the light from a VCSEL array with a single shot image. The information enables the analysis of each single emitter in terms of absolute power within a very short time frame, enabling stuff like defect detection even in the production. The system is optionally equipped with two things. So one comes with a fiber output and one without the fiber output and one with the fiber output with a translation stage as well. So which only moves the optical parts so that you don't have to reposition your DUT during measurements. And with the fiber optics that are attached, you can have an additional high resolution spectroradiometer, which then enables the analysis of the spectrum for each single emitter on the array. The VTC 4000 allows to measure a series of images of the VCSEL array in order to get all the optical parameters of an array, such as X and Y positions, focus position, absolute power, polarization, numerical aperture, the beam waste, the M² value, and so on. So together with the spectroradiometer and the translation stage, you also have the possibility to measure the spectrum of each individual emitter, and that can be characterized including the peak and the centroid wavelength. So here you can see that you have the set of emitters, and you can, with the help of a translation stage and the high resolution spectroradiometer, you can measure the centroid wavelength, the peak wavelength, the spectrum of each single emitter. Yeah, one of the most unique features of the VTC 4000 is its capability to measure polarization corrected absolute power. I mean, we know that each emitter within an array and within itself will always show different kinds of polarization. Hence, it has become extremely important to account for it while you're measuring accurate absolute power, especially for values, determining values for laser eye safety classifications, for example. So the innovative calibration concept of the VTC 4000 is based on a flat field and a polarization correction. The polarization correction actually takes place in the form of an inline analysis of the emitted light and corrects the polarization dependency of the entire optical system. So this calibration enables absolute measurement of power and polarization properties such as angle and degree of each single emitter within the camera's field of vision in a one-shot process. And this can be very helpful to analyze and characterize, for example, polarization controlling techniques. And this unique measurement concept actually guarantees a very minimum error budget in absolute power measurements and results in a very high measurement accuracy, as currently actually offered by no other near-field VCSEL measuring systems. Of course, no hardware is complete without a software, so we have a software as well. In Lumi Suite, we offer a very robust and flexible image analysis software suitable for lab as well as production line. So we have the SDK that further empowers the VTC 4000. And to conclude, to give you some statements and to take some points to take home, the VTC 4000 in a nutshell, it's a near-field camera specially developed for ultra-fast, precise 2D analysis of VCSEL arrays, especially at the wafer level in production lines. It enables polarization control characterization of all relevant parameters simultaneously for the single emitters of the array. And thanks to the unique calibration concept, 2D quality analysis is performed with unprecedented measurement accuracy. And like all of our systems at Instrument Systems, the VTC 4000 is traceably calibrated to national standards like the PTB or NIST and delivers measurements with absolute precision. That's my time, guys. Thank you very much. And yeah, I'm ready for questions if you guys have any.
Thank you very much, Karthik. Please remember you have to contact all the speakers if you want to get in touch with them. info@instrumentsystems.com. Karthik, obviously it's an epic meeting, so the first question is obvious. It's the epic question. What can you do for the other 749 members, and what can they do for you?
Yeah, so it's basically, as you pointed out at the very beginning of the meeting, so this is a product that is very well designed, or specially designed to integrate it into production lines. So it's something of a product that is easily integrable into system or integrators. So that's what we are looking for. We're looking for system integrators who are basically also responsible for the entire manufacturing processes of the VCSELs, be it also at the wafer level or after the chip level, or even at the end user, at a smartphone of the end device as well. And we are exactly looking for such kind of system integrators because we provide a lot of these one-shot solutions which are ultra fast, tailored for production. So example, polarization measurements, we all know it's not so easy to do it in a one-shot measurement. We all know the linear filter, a linear polar filter, and putting it in front and then moving it. So a lot of mechanical parts going in. So we, with this unique capability, we have the calibration concept. The VTC 4000 has the capability to give you a one-shot polarization corrected measurement. So it's basically very tailored to production environments and mass production.
It is all about the polarization. We are talking about large arrays of pixels in which every pixel can have polarization problems, not only the degree, but also the angle. I would like to see how this could be relevant for the industry. And lucky for you, we have one of the key people in designing optical systems based on active and passive imaging. And that is no other than Frank Burowski, CEO of LightTrans International. Frank, thank you very much for joining today. What's on your mind?
Yeah, I think first it's a very, very great talk here and very good product. I'm very fascinated that you are measuring with polarization included. And we should talk with each other soon because we are, of course, very much interested to get measured data with polarization included, measured data from VCSELs, which we can use as a source model inside our software. And that seems to be very clear because applications of VCSEL become more and more broad and more interested. So the better we can put the data, the measured data in for the modeling, the better, right? So, and here we have two innovative levels because we can do something and you can do something and we can put things together. That's quite cool. So really, that's interesting to see. Can you deliver data for modeling? I think so.
Yes, absolutely. Yeah, absolutely. Thank you, Frank. Yes, I mean, I agree. It's the applications are getting by the day, by the hour for VCSELs more and more. And of course, the talk about polarization controlling techniques on the VCSELs has been going on for a long time. And slowly now we're at a point where the manufacturers are also getting into the production environment with such controlling techniques as well. And I'm sure that I mean, the innovative concept is basically, as I said before, is tailored exactly for those kind of reasons that you mentioned. And yeah, sure, we can of course provide data, and yeah, we should definitely get in touch.
Absolutely.
Yeah.
Thank you very much, Frank. One more thing for you, Karthik, before I let you go. I was quite fascinated by the fact that you developed this product in two fashions. One is with fiber couple and one without. And the point of the fiber is to connect it to a high-resolution spectrometer. This is a demand from your customers. How do your customers use your device in combination with a spectrometer?
So it has been a demand for our customers as well. For for many reasons, especially for the reason that to see the wavelength. So we had some of the inquiries that came up was to see the shift of temperature versus wavelength of the VCSELs. We know that it's not so sensitive. VCSELs are not so sensitive. So that was one of the requirements or one of the requests. So we do, that's right. But in a production environment, using a translation stage and then the entire scanning the entire VCSELs can sometimes be a bit of a blocker. I wouldn't say a blocker, but bit of a stretch. So such systems are very well designed for Q&A purposes in the reference stations. And then we also have the one without the fiber output where you just get the peak wavelength, as to say.
Do you need to have your VCSELs tested at wafer level with one-shot picture and measure the polarization? Can you maybe help instrument systems address other more flashy wavelengths in different ranges? Contact my friend Karthik Lear. Really fantastic presentation, and this product is a really rock star, a real rock star. Like a rock star is the next presenter, Stefano Bonora, all the way from Padua, Italy. He's going to talk to us about something that is booming right now. In Europe, we have the best optics. You know that. We're going to talk about adaptive optics. We're going to talk about deformable mirrors, and most important, we're going to hear about the new new deformable mirror by Dynamic Optics. Grazie mille, Stefano, for being with us. We go all the way to Padua. We want to hear how we can help you. We want to hear how we can integrate that deformable mirror. The floor is yours. Not that Bert, but the deformable mirror. Let's try.
Thank you, Jose, for the nice introduction.
We still cannot see your screen. Let's see now. Let's open the PowerPoint. Okay. Yes, perfect.
Yeah. Thanks, Jose, for the introduction. So I will introduce you dynamic optics and a new type of deformable mirror with embedded tip-tilt stage. Dynamic Optics is a company located in Padua, north of Italy, and it's a spin-off company of the Institute of Photonics and Nanotechnology, and was born in 2017. And it is participated by a larger company, which is called Officina Stellare, which is a space factory of optical components that we collaborated with. So what about our technology? So our technology is based on the use of flexible glass membranes that we use in order to create flexible optical devices. So we can design both deformable mirrors and also deformable lenses. So the talk of today is about deformable mirrors. So let me spend at the beginning just one slide about deformable lenses. So our lens is a patented technology that is used mainly in ophthalmic instruments, microscopy, vision science, or laser communication to improve the performance, the optical quality of the instruments. And the concept of using a lens to correct for optical aberration is that you can it's really plug and play. You can screw it up on your microscope objective, and then we can supply an automatic correction software. Just a couple of examples. This is a light sheet microscope image of a mouse brain, and you can see after the waveform correction that the image has a higher contrast and also a higher resolution. The same way we can also use our lenses as they were deformable mirrors. The same way we can use it for telescopes in order to correct for optical aberration, and you can see an example. But now let's move to the main product that I would like to present today, which is a deformable mirror. So our technology uses piezoelectric actuators that are bonded to a glass substrate. The glass substrate can be coated with any type of coating, metallic or dielectric. So it can be used, this is very important, can be used with really any type of laser, picosecond, femtosecond, or CW up to 4 kilowatts. And we have been supplying systems to many institutes and companies in the world so far. And the main applications are in the high power laser control, again with pulse and CW laser, also for astronomy and free space optical communication. So what's new today? So we added to our standard deformable mirror. In this case, this is a deformable mirror with 64 actuators with 64 points of deformation of the glass membrane. We added a tip-tilt stage, which is integrated, so we can control both the pointing with a very high accuracy and very high extension, also aberration. So in this movie, I can show you now that we will use on the top, you see the deformable mirror with 64 actors generating some shapes, and the typical stage moving up and down the PSF that you see on the left. So at the beginning to start, we are seeing now, for example, a cylindrical wavefront, and the typical stage can move it around. But we can also create, for example, coma. We can create really arbitrary shapes. So this is coma. It is rotating according to the typical stage. And the response time of the system is in the order of milliseconds. So to conclude, I would like to give you a couple of application ideas. The first one is in the field of laser comm or astronomy, which are basically sharing the same infrastructure. So in this case, this is a product that we developed in collaboration with our partner company Officina Stellare. So they developed the telescope, and we integrated the deformable mirror at the place of the secondary mirror of the telescope. So the system was tested. I'll show you a test using a star, but can be used also for single mode fiber coupling. You see that when the turbulence destroyed the creates aberration, destroy the beam image of the star, while when the system is on, the correction is completely removing the fat of the tube. The second application is a completely different field, but in this case, the instrument is the same. It's again a deformable mirror. So let's start with laser that we can well focus on our target. What about using a different beam shape in order to carry out some laser processing on the surface of our material? So I can show you in this slide that we can generate from this focus point a square top hat profile, and we can rotate this top hat profile. We can transform it into a Gaussian profile or as well a round flat top. So all these beam spots intensity distribution can be used in order to improve your laser process. So we are working, trying to develop different collaboration in this field, and I conclude just giving you an example of laser marking with an elliptical spot shape with a deformable mirror. In this case, we were using a 40 watts femtosecond laser beam emitting at 30. And we tried to carry out the laser marking using an elliptical beam spot shape and changing the beam spot while the laser scanner was changing its own position. So you can see here with a low rep rate, you can distinguish the spots which were changing shape. In the second case, we are, for example, rotating the elliptical shape, and you can see while scanning with the laser. And in the third case, and the same, but changing the speed of the laser process. So you can see that really we can carry out new functionalities to your laser, just adding a deformable mirror and a control software. So to conclude, our deformable mirrors can have a very high stroke, more than 40 microns. They can be used with any type of lasers, CW, and also pulsed. We tested our system with the laser up to 4 kilowatt of average power. The response time is pretty fast, it's in the order of the millisecond. And now we also have integrated a new functionalities, which is the tip tilt control of the beam point. So thank you very much for your attention. We are very open to any type of collaboration, so feel free to contact me for any idea.
Thank you very much, Stefano. Stefano.bonora@dynamic-optics.it. I'm very impressed with this presentation. Really fantastic work. And let me remind everyone, these people can actually do very large size optics all the way to 200 millimeters, and they have optical quality enabling a stir ratio of higher than 0.9. This is very, very high quality optics that, thanks to being reformable, they can be used in beam shaping. Stefano, you know what's coming? It's the epic question. What can you do for the others? What can they do for you?
So, of course, what we can do for others is to supply new technology that is relatively unused in the field, for example, of high power laser and beam shaping. And I think this is very, very promising because we can really just adding a component to the laser system, carry out really new functionalities. So what I expect from others is that I will receive ideas for new applications. We are really a small company, so we are very open to support any type of innovation and any type of collaboration to carry out new tests.
And one of the others is in the room today. We have the company SUS Micro Optics all the way from Neuchâtel, one of the key companies producing wafer level micro optics. Wilfred, thank you very much for being with us today. What's on your mind?
Yeah, I just wondered how many, the classic question for adaptive optics, how many Zarnickes can you correct, and can you do them orthogonal corrections, so only correct for one Zarnicke, or do you correct just the whole? You have a wavefront sensor. Can you distinguish the Zarnickes then as well, or is this always?
I mean, we can provide the whole system, including the formable mirror and wavefront sensor and control. So the number of modes that we can correct depends on the number of actuators. For example, in the formable mirror that I've been showing you before, the 64 actuators can really realistically correct about 50 modes in terms of Zarnicke description.
Okay, great, very impressive. So and can you handle high powers when you have a glass? I mean, if you said 40 watts, that's quite a bit, huh? So.
So the power depends, of course. I can divide the problem into two categories: pulsed and CW laser. In terms of pulsed, the main thing is that we use the same coating that you're using in your laser system. So I'm sure that we can apply any type of coating. So we can realistically think that we can cover any type of request. In the terms of CW, maybe it's more complex because average power can be an issue. So we tested our deformable mirrors to 4 kilowatts, and we are open to collaborate to test it to a larger power level.
The next question in the room is coming all the way from Jena, and it's coming from Frank Wirowski from LightTrans.
Okay, hello. Stefano, I have the question. Of course, if I hear adaptive optics or special light modulators related story, I'm always interested in how I can put our software when we design something for fast prototyping or something into this, or even to have a feedback loop. So my question is, will you offer or do you already offer an interface, a data interface, so that we can address your deformable mirror to achieve something we have pre-designed, and then maybe to use it as a starting point for a dynamic optimization in the system itself? So a little bit the question I said before, source data in, and now I give fabrication data out.
Yes, of course. Before starting, everything must be simulated in order to be properly designed. So basically, yes, we often supply also service. So we don't really supply only the components, but we also carry out a lot of design on the application that our customers ask to us. And this can also done by your software, which is very powerful. So maybe if you would like to have an open question that your software can deal with is, how can I determine the waveform that generates a certain beam shape? This is a still open question. We have some methods, but we know that they are not, that can be improved.
No, that is one application, but I think it's in general very interesting for us in the context of freeform services and so on, that we can test something as fast as possible. I think that has a big future, right? Even if it's maybe not as accurate, but for prototyping to check something, it's great, right? So we should talk.
Deformable mirrors at any size, any shape, and any angle of incidence. Amazing work, and really amazing work by Dynamic Optics. Stefano, thank you very much for being with us today. And let's go all together to Jena to hear now from Frank Wirowski. He chose this platform, EPIC, to present his new product, seamless transition between ray and physical optics modeling. Everybody knows Frank Wirowski. He's one of the iconic people in optical design. LightTrans is a success story of Europe. Thank you very much once again for choosing EPIC to show this new product. The floor is yours, Frank.
Yeah, it's of course a software typically is not always a new product, but also very often just a general development, and development is never ever ready, right? That's the point. Software is never ready. So go to the start. Okay, I think everything's fine.
Perfect.
Okay, great. All right, then let's start. It's 5 to 7 minutes. It's not a long time to talk about the breakthrough technology we are using behind virtual lab fusion. I just like to say there's a lot of theory behind it, and I like to make it as compact as possible. Our motivation, our general motivation we have is that we feel that there's an increasing demand for optical modeling and design in a more general theoretical and algorithm framework. So that means people are really interested in to understand how to go out of this ray optics bubble we are all in optical modeling and design, because there's more and more pressure to go beyond that. For example, because of the sources. Let's talk about the VCSELs before, about macro and nanostructured surfaces, even sometimes freeform surfaces, miniaturization, and in general, there are more and more variation in the application, the use cases, and the scenarios people like to do. So there is a pressure in the bubble, and we know how to overcome it. We must go to the superset physical optics, because physical optics includes ray optics. So if we like to go out of this bubble, then we need to do it. The trouble is that in praxis of optical modeling design, ray and physical optics appear deeply different. You all know that, right? Even in the software packages. So it's deeply different. And the question appears, of course, why and how to overcome that? And our answer on the first level is, of course, the light representation itself. In physics, we deal with objects, and we need to describe the objects in a mathematical and computer way. And ray optics is described by ray parameters, position and direction, and flux, maybe. And physical optics is described by electromagnetic fields. And that is quite different on the first look. But if you like to unify that, if you like to get the common ground of it, then there is no chance to work with rays. Then we must, of course, work with a more general concept of electromagnetic fields. And then maybe some of you think what the guy is talking about, how to use ray optics with fields. That is not quite new, I must say, because we are looking for something in physical optics which is related to ray optics. And I'd like to give you a citation by quite some important people, Born and Wolf. And they say already in their book, that we are looking for geometrical laws relating to the fields. So we are interested in geometrical laws related to fields. So that means we exactly follow this suggestion by Born and Wolf and try to do that. And let's do it very fast. Ray optics propagation follows Fermat's principle. Physical optics propagation follows, roughly speaking, Huygens principle. You know that. What is the essence between them from a mathematical point of view? The essence between them is that the Huygens principle, if you put an input field to an output field, then it's an integral relationship, like a convolution. Whereas the Fermat's principle is a pointwise relationship. That means if we go to the essence of the difference between physical optics and geometrical optics in terms of electromagnetic fields, it's mathematically the difference between integral operations and pointwise operations. That is finally the big difference which we need to care about. And that's exactly what we are doing in virtual fusion, in our theory and in our algorithms. And the cool news is the transition between both domains, the integral and the pointwise electromagnetic field description, can be controlled completely in a mathematical way. And that is extremely, extremely important. Now, what does it mean in praxis? In praxis, it means, let's assume we have a source and we have a source field. So we measured it together with our friends to the VCSEL measurement. And then we have a component. Let's assume it's a freeform mirror or whatever. And this component must be modeled in physical optics. That is what we call a solver. So we have a solver. These solvers can be integral, for example, Fourier modal method, beam propagation method, LP solver, me solver, etc., etc., etc. These are what we have on board in Virtual Lab, or pointwise, like for example the S matrix or the coating matrix in the K domain. They are pointwise. So we have integral operators and pointwise operators. And now we need to connect them, because connecting solvers, that's our technology. And this connection is free space propagation. And in free space propagation, you know it all. We have all our diffraction integrals. They are all included in Virtual Lab in a very smart and fast way. But we can also do it pointwise. We can also propagate pointwise fields. And in this logic, we can build up full sequences or full trees if you do non-sequential modeling. And then we have a lot of connected solvers, free space solvers and component solvers. For example, let's assume we take some special components like grating and the lens. The grating uses an integral solver, the lens uses a pointwise solver.
And then we are using the free space. And then let's assume we have here, we can do it automatized. Virtual Lab is doing it completely automatized or pre-configured or completely customized. So you can do any level. If you have no idea about, then just leave it to Virtual Lab. And then, for example, you get a pointwise here in the first step. And then from the grating to the lens, you are in the far field maybe. And then from the lens to the focus, maybe you use the Debye integral. So that means Virtual Lab decides it for you, or you decide it because you know what's going on. Okay, now, and the clue now is, if all these operators are pointwise, all of them, from the beginning to the end, and if that is justified, then we can take just the coordinate mapping from the input to the output, and then you get, in fact, the input points and the directions and the output points and the directions, and that is what finally leads to ray optics. This is how ray optics is accessible and included, by the way, on the higher level in physical optics. And that's how we do that. That means we are using physical optics, but then we can go down to ray optics. I'd like to show you at one example at the end of the talk. The physical optics we call, in comparison to ray tracing, field tracing. In the new version, we have introduced in the last version, which we now will be included now in the next one, more and more, is our modeling control panel. You will see ray tracing and field tracing. And I'd like to show you how that works at the Mach center interferometer, which is a nice example to show physical optics effects, of course. So here it's our build up of the system by the components. Here's a 3D system shown with a few lenses and some mirrors and so on. And now I start to do ray optics. So I go into this subset, but I use pointwise operations in physical optics, but I skip all the field information. I just use the mapping. I just use the coordinates. And then I get this result, clear. It's a 3D ray tracing picture, very nice. Now I'm interested in the dot diagram in the output. So I do that, again with ray tracing, but now I push this button here, and then I do it, and then I get this result, which consists of two modes, of course, because I have two branches, right? And then I go to field tracing. That means I don't reduce to the ray information, but I take all the field information. And then I get the interferogram just pointwise, and that's this result. You will see this result takes also just a few seconds. It's very, very fast. So you get this result. And I'd just like to show you another example here to see how we handle different coherences. I take a RGB source, so red, green, and blue, plane wave. So I change the source. Then I do again ray tracing, and then I do field tracing. And in field tracing, I have three colors with three interference patterns, and Virtual Lab knows, because of physical optics, it knows that the colors are incoherent, but the same color is coherent to each other. And so you can here model white light interferometry and so on. So that's what we are doing, and I'd like to give you at the end a very short insight how that looks like. Okay, now let's do what we have seen before in the PowerPoint. So here we have our system. Now, let's start with the rays in the system. And here we get the result. So we have our 3D system and can now work with that. So next we do ray tracing. Here we have the dot diagrams, very trivial, with the two modes, one of the one branch of the interferometer and one of the other one. And now we switch to physical optics, just taking the next button. And here we have restricted with the number 1 to a pointwise modeling, which is enough here. And here we get the result. So we get a full interferometer by physical optics modeling. Now let's make it a little bit more complicated by changing the source. Now we have the RGB source here. And do the same. Do first ray tracing. Here now we have the 6 fields, 6 modes superimposed, color and the coherent part. And now again, we do field tracing. Now we have 3 times the calculation time of before, and but still very fast here to get the result with the superposition of the different interference patterns from the different colors. Okay, so that means Then I'm finished with that. It means our strategy is to connect solvers. And by that, we are using the basic mathematical distinction between ray optics and physical optics, but all in physical optics, which is integral versus point-bus operations. That allows us to include ray optics easily, and that enables fast physical optics. Thank you.
Thank you very much, Frank. Very, very impressive when you can do the ray tracing, the weight tracing, and the field tracing in one hand. I was actually quite surprised by how fast is the simulation. There you have some idea, you have something to share with us, because that was really, really impressive. I've been doing optical design in the past. So how fast is the combination of ray, wave, and field tracing?
How fast?
Yes. How fast can you do the simulation? I was very impressed with how
you
fast
saw it. You saw it.
Yes.
You just saw it. Yeah, that was as fast as you saw it. What should I say?
So you have an entire community who wants to. Yes.
But of course, if the physical optics becomes integral, then ray optics is not allowed anymore. And then, of course, physical optics can become slower. But it's still typically quite fast because we have one trick, and that's the FFT. And FFT is an integral operation, but linear in n. And that helps us a lot. I'd just like to comment on that. People know ray tracing is fast for lens design, but it's slowly for Monte Carlo ray tracing. Monte Carlo ray tracing is super slowly. Monte Carlo ray tracing is using also an integral concept because one ray is becoming a lot of rays. It's like Huygens principle, but it's doing it in a random way, which is not smart, not using the FFT trick. So we are even faster in scattering than. I had no time to show that, but that is even the case. So we can even be faster.
To remind all the optical designers in the EPIC network that there is a way to do a trial of the LightTrans software, correct?
Of course.
So you want to use
virtual lab. LightTrans is this company.
If you want to use virtual lab, there is a free trial. Wilfred, one of the optic gurus in EPIC, what's on your mind?
Thank you, Frank, for this nice overview. Of course, we have been using your new version already. And we're still trying to figure out what are these different modeling levels. I don't know if you have a minute to explain this here. I mean,
the third level?
I have to confirm it has become really fast, but there's still a learning curve behind. It's not as easy as it always seems. We are working hard on it in the next version, which is coming this month. To make it easier, and we have an assistant, so you will see it will be very, very smooth and very easy to understand. Okay. The point is sometimes also this kind of talks here are very helpful for me and for our developers, because to bring that in 5 minutes down on the key, it's not easy, right? Churchill, greetings from Churchill. So it's not easy, and that helps us also to understand how to communicate in the development and how to communicate in the help and the assistant system of the software and how to display it in the software. So I had a lot of ideas in preparing this talk. How to Christian, our chief developer, is listening now, and he knows it already. So and now he heard you. So we will make it easier to get it.
I recommend all the optical designers in EPIC to have a look and a trial of this software. The virtual lab is really very easy to use, and it's also very easy to get access and to get help from the LightTrans company, and that what also makes you unique. Frank, thank you so much for being EPIC. And let me continue. The laser community is very strong in EPIC. Hence, the laser optics community is also really strong in EPIC, and all those laser optic community have all a problem. The measurement, the accurate measurement of laser-induced damage threshold. In EPIC, we have a service for that, and that service is from Lidaris in Lithuania, in Vilnius, Lithuania. I'm going to the capital of lasers in Europe, going to Vilnius. I'm meeting Linas Esmalakis, scientific director of Lidaris. Thank you very much for being with us today, and tell us about this new service, laser-induced damage testing, a continuous wave regime. The floor is yours.
Hello, Jose, and the members of EPIC. I'm very pleased to present our new product. It's quite an unusual product in the sense of it, but I would like to introduce you to laser-induced damage testing at continuous wave regime. So to give a short overview of what Lidaris is, it's a relatively small company, but it has almost 20 years of experience in LiDAR testing. As mentioned, in the small capital of lasers in Europe, Vilnius, Lithuania. So we serve the global market in laser-induced damage threshold testing. We are also active participants in the LiDAR research community. We have won many awards at scientific conferences, For example, we do laser damage testing for a thin film damage competition organized by Livermore Labs. We also heavily invested in space optics lifetime estimation in our projects with the European Space Agency and so on. So to give you an overview of what we do, our product is basically a controlled distraction of your optics. We have three main ways that we work with our customers. So first of all, we do standard ISO-based LiDAT testing services. So it can be a simple one-off LiDAT damage level measurement results. We have one of the widest ranges of available irradiation conditions in the industry, and we provide detailed reports that are well regarded in the industry. What we also do is custom and dedicated LiDAT services. So we integrate in the manufacturing process of various companies, and we offer extremely high throughput and fast turnaround for testing various manufacturing batches and so on. And the final way that we do our work is a project-based R&D service. So when you encounter some problems in your designs, it's usually with extremely powerful lasers. We are here to help you, and we design custom LiDAT testing setups and custom protocols to address your problem specifically. So our toolbox includes standard damage testing techniques provided by the ISO standard. So single pulse damage testing for quantitative defect density estimation, SN1 test for lifetime estimation of your optics, pass and fail test, which is a great non-destructive qualification test to evaluate whether your optic meets the standards requested by your customers. And we also offer a non-standard but still widely used test in the LiDAT community. So RN1 test, which can be used for extremely small samples, raster scanning, which I will talk more about today, which helps to find even the lowest density defects in your optics and adjust it's extremely popular with extremely large aperture optics to determine their LiDAT. And we also offer custom LiDAT testing, as I indicated in the previous slide, for example, for any customer R&D projects. So most common LiDAT testing conditions that we offer range from the UV to the near infrared. We also offer from continuous wave to femtosecond regimes. We have vacuum and cryo options. So as I mentioned, that's one of the widest selection that you can find in the industry. So what I'm to present here today is the continuous wave testing regime that we have installed in our labs. So we offer continuous wave testing at near infrared with up to 6 kilowatts of laser power. We offer the previously mentioned protocols of certification, so pass-fail test, T-on-1, so time on one on a single site. So it's equivalent to lifetime testing at pulse regime. We offer also RT-on-1 tests for small optics and raster scanning tests for detecting the extremely low density defects. So I would like to talk a bit about the raster scanning, which is becoming extremely popular as it mimics the real application conditions in the real life. So in the continuous wave regime, we are mostly concerned with highly absorbing particles or defects of your optics. So there are two ways that these defects can destroy your optics. So first of all, they can come from manufacturing. So as you can see, there are various subsurface damages during the polishing, the building layer, the various absorbing particles that left from the polishing agents, and also any coating defects such as nodular defects and so on. Or they can also be any particular contamination. So, for example, even the packaging of your optics or handling of your optics can be detrimental in the continuous wave regime. So one of the tests that we offer is the so-called raster scanning. So what we do is we basically use a well-characterized laser beam to scan your optics with a uniform irradiation level, and we repeat this procedure with the increasing irradiance, and we find some. We also image the scan area with automatic microscopy, and we find the defects in your optics. So we repeat this procedure and register all the events that we find until your optics is catastrophically damaged. So as you saw in one of the slides, you can basically have a huge hole in your optics. So what this helps us to do is to define the initiation and catastrophic damage thresholds for your optics, which you can see here. So for the initiation, we usually detect extremely small changes in your optics, which is extremely important for high radiation facilities where you do not want any initiation on your optics at all. And we also define catastrophic damage thresholds. So for example, if your laser can tolerate a few initiation sites, or maybe you have some sort of policy in replacing your optics periodically, you can try to keep your irradiance below the catastrophic threshold while we're still working in the initiation regime. So what we also provide for our customers is detailed report on the size distribution of the found initiation sites on your optics, which is extremely helpful for our clients that try to understand where the defects come from, and what's the distribution of the defects, what's the validity of them, and so on. So with that, I would like to offer you our services because we are still extremely interested in damaging your optics. So please get in touch if you have any problems with that. Thank you.
info@lidaris.com. Acho, thank you very much for a great presentation, Linas. It is great to have you in EPIC, because we do know that the laser-induced damage threshold characterization is very, very complicated and a big challenge. We have 750 EPIC members listening to you. What can you do for them? What can they do for you?
Yeah, so as I mentioned in one of the slides, what we can do for you is damage your optics. So it's better to damage your optics inside the lab so that you don't do that in the field. So that's our main goal. And what can EPIC members do for us? We are always interested in extremely powerful yet well-behaved lasers and various measurement equipment such as cameras, energy meters, and so on. And we are also always interested in any research possibilities. For example, because we usually work with state-of-the-art projects, and we are not scared of challenges, but we are searching for it actively.
One of the key companies who could be interested in you damaging their optics is mid-infrared optics supplier Iridian, who provide mid-infrared filters and mid-infrared optics. And Jason Palivar here with us. Jason, what's on your mind?
Thanks, Jose, and thanks very much, Linus. Very, very interesting talk. Yeah, normally we don't like to wreck our filters, but we do need to do laser damage testing periodically on filters under different conditions. So 2 questions. You mentioned fast turnaround time, so interested in what is a typical turnaround time. And the other thing you mentioned in your talk, on one slide, you mentioned space optics lifetime estimation. So I'm curious as to about what aspect of the testing. What are you providing there?
Yeah, so we try to guarantee our turnaround of up to 2 weeks as the largest option. As for the lifetime estimation for space optics, we are very interested in various damage modes that we observe during the LIDT testing. So what we are working on is separating the various damages that we detect into color change damages that we see, and also catastrophic damage, and in the fatigue effects of these different damage modes. So yeah, what we find that we have developed some sort of we have developed protocols that helps us to estimate the lifetime distributions of the damage size that we can use to estimate and extrapolate the LIDT of those optics. So, for example, we usually need to estimate the LIDT of optics, let's say for 2 years. 2 years in space, but we have techniques to do that when doing tests only, for example, for 1 month, so on.
And we go from Canada to Switzerland. Wilfred Null from SUS Micro Optics. What's on your mind? Do you want them to wreck your optics?
Yes. No, we don't, of course, but we do beam homogenizers since 20 years for high power lasers. And there's always a question: how much power can you put on our elements? So we regularly have this question by our clients, and what we see sometimes, it's so we can perfectly clean our surfaces, but sometimes you never know if you still have subsurface damage. So the question is, which you cannot see. So you never know if you have these subsurface damages or not until you test it on the client side. So, and usually we are okay. We never had any issues. So, but I'm just curious, how can you test these subsurface damages with your system if the surface is perfectly clean? And the other thing is coatings, obviously. So we have to do air coatings on our things. So sometimes it's not the material itself, but the surface coating that gets damaged. So this is also an important subject for us.
Okay, so for the subsurface damage, since we are not searching for it optically, well, most of the damage actually occurs from the subsurface damage and cracks and so on. So by doing the raster scanning procedure that I just showed you, it's usually a good way to detect that. So I'm not sure if I'm answering your question correctly, but for the AR coatings, yes, so that's usually the case that the coating is the limiting factor of the optics LIDT. So we do testing for HI, AR coatings, also for metallic coatings and so on, as well as for substrates. So
thank you very much, Wilfred.
Okay,
yes, please go ahead.
Okay, so for the subsurface coating, it's usually not absorbing, but it creates intrinsic stress in the material. So so it's laser induces more thermal stress into material, maybe, and then you have a stress propagation in the material. So and this is sometimes difficult to detect because there might be nonlinear behavior. Okay, let's discuss it offline, maybe. Okay.
Indeed.
Sorry, Jose.
No, never apologize to me for making the meeting great, Wilfred. And we want to say that if you are comparing different suppliers of laser optics and you want a company to really test the laser-induced thermal threshold, it is the company to choose. Lidaris, ultra fast turnaround time. Today they presented CW LIDT testing. And we continue with the meeting. We stay in Switzerland, Wilfred. We stay in Switzerland because now we're going to meet Patrick Rufos and Eugen Bauerbold, who work for MPS Micro Precision Systems, the company that can provide motorized and ultra-high accuracy positioning systems. We want to talk to them about the SEAL linear lens actuator. Thank you very much for choosing EPIC to deploy this new product to the industry, the floor, and the attention of everyone goes to MPS.
Hello, everybody. Thank you very much for this opportunity. Do you see our screen?
Not yet. Please try to share it again.
Okay. I thought it should be okay.
Yes, we can see your screen clearly.
Okay.
Yes.
Just took some time. Okay. My name is Eugen Bauerbold. I'm responsible for sales in Europe at MPS since 1 year. And we are 2 people, my colleague Patrick. I will present you what MPS is doing, the overall scope, just a short overview, and Patrick will show you our new development. So MPS initially came from the ball bearing industry, was founded in 1936 as a miniature ball bearing manufacturer. In 1948, there was the first ball bearing for the watch industry developed, and since then it's developed and supplied by MPS. So the MPS group belongs to the Faulhaber group, and we are divided, or we are in 4 parts. One part, big part, is the watch industry, like I said, the bearings, the gears, and all the stuff for the Swiss precision watch manufacturing. The second part is MPS Micro Systems, where in which part we with Patrick are located. And then we have a part which is called MPS Precimet. We do manufacture orthopedic instruments for the surgeons. And one part is a precision Swiss turning parts manufacturing company. So like I said, we started with the ball bearing manufacturing in the past. And later then linear bearings and some ball screw you see on the back on our roll-ups. The idea is to have some really smooth systems with low friction and no stick slip, but also that you really can make some precise movements of just some microns or even less. And this is the base for our product. So we develop with 14 engineers in our development department complete systems. That means motorized systems like zoom function for focus function or tilting mirrors. Here you see the smallest hexapod in the world, where you see 6 legs and one. The precision of one leg is just plus minus 1 micron. Just the main business is based on these systems which we develop with our customers together, and one of which Patrick will present just right now. This is where we are working is the medical field. For instance, the active implants. This is one artificial heart where we produce the pumping unit. Then the optics and photonics industry, the automation where you need really a high precision. For instance, the PCB assembly, aerospace and defense, and a big part is also the science. And like I said, we are 15 engineers just developing innovative new systems. We have the competence of assembly. We have a very deep production knowledge, also department, and also knowledge. We have maintenance-free systems, and of course, quite high precision and mostly customized systems. So now I will give over to Patrick, and he will present you our new.
Thank you, Adrian. Now we'll present you our new development that we've achieved here at MPS Micro Systems. It's a linear lens actuator, which has a specific feature of having the drive mechanism totally sealed with specially designed bellows for this actuator. The idea here is to avoid any contamination that could come in and out of the system in the purpose of use in, for example, highly clean environment, like it's often the case in optics. The system is based on ball bearings, on ball screws, low friction ball screws and ball bearings, and is driven with motor Faulhaber X4. It's a brushless type motor, so we have an encoder, and the regulation is made in closed loop. So we can achieve a stroke of 40 millimeters with that actuator. And we measured a Z position repeatability of plus minus 4 microns for this system. Another point which is interesting in this device is the fact that we try to optimize as much as possible the width of this actuator to allow kind of molecular system to allow stackable mounting of them. So you can put them side by side in the idea of realizing more complex optical function, where you need to have several lenses moving to realize an optical function. On the right part of the slide, you can see a typical configuration that has been realized for high power laser cutting application. The idea here is to have a zoom system with three lenses in order to shape the beam spot, and as well as the location of this beam spot inside the Z-axis, the optical axis. What I would like to emphasize in my last slide is the fact that we are really, at MPS, we are not realizing standard product except ball screws on ball bearings, but we are focused on the realization of customized solutions. So here, for example, if this actuator seems to be a good solution to your development, or could solve a technical issue because it's from its modular approach. We will totally adapt this actuator to your system. For example, for the integration, we could change the stroke as well. The motor selection, here we use a brushless one, but we could, of course, use a stepper one. The encoder as well. Here it's directly it's mounted directly on the motor, but we could imagine to have the encoder directly fixed on the carriage to have better positioning repeatability. So we have different approach, different options to realize a complete solution that will fit the requirement of the application. Of course, the shape on the size of the different lens holder will be modified corresponding to the lens diameter on the position, the reference position of themselves. So to allow to perfectly fit to the optical design. So yeah, that's it. Yeah, that's it. Thank you for your attention. And
thank you very much.
Gregory Bagnot, Patrick.Rufus, and Eugen.Bauerwald at mpsag.com. Thank you very much for being with us today. I have, of course, to ask you the epic question, but first I had to say, wow, 40 millimeters travel with 4 micrometers accuracy. I am amazed, truly amazed. I have 750 epic members, 750 epic members behind me. What can they do for you? What can you do for them?
Yeah, thank you. Of course, we know this is a great question from the epic side. Yeah, like you see, we are the specialist in the mechanics. We are no specialist in optics. So all the products we develop with our customers together, and that means also what you see is just one example of, I don't know, hundreds of different shapes, different systems. Not only with ball screws, it can be some flexible elements, whatever. But anywhere where you have some system and you need to move somehow to have a really precise mirror tilt, to make this zoom function with one lens, several lenses, or whatever, we will be glad really to develop something with you together. We have a big team, we have a big knowledge in a project management, where we have weekly meetings to work with customers together. What did we reach the last 7 days? What maybe should we have a compromise somewhere? So also some inputs from the customer, maybe some ideas where we really work closely together. And yeah, this is where we are looking for such a projects. And of course, if you already have maybe some existing system where maybe some need optimization or whatever, we really have a huge experience in moving micromechanics. Yeah.
When I see this slide, I really loved it, the way that you actually made that arrays of lenses. Could you comment on the speed? So you guys talk about how accurate and how long is the travel. On the speed in which you could actually move the lenses, is that an application field perhaps for the camera or for the laser companies?
It was in this modular approach, we saw more to the precision, I mean the accuracy and the repeatability of the positioning of the lenses. And here the nominal speed was set to 80 millimeters per second. So it's fast, but it's not like in dynamic optics, for example.
It's not for every application. Yeah, first we thought about high power laser cutting of this system, where you have this high power. It has to be sealed that no dust or whatever can come on the lenses, and then some damages can happen. Yeah, 80 millimeters per second, but of course 40 millimeters, it's also not maybe so many applications for such a long stroke. So like we said, it's customizable. You can do just 10 millimeters and so on.
The most accurate company in epic positioning and motioning arrays or individual lenses is MPS Micro Systems. I am amazed at the kind of things they can do. Most important, this was not a product only. This is a way of provide customized, fully customized solutions for every particular challenge. And remember, 40 millimeters plus minus 4 micrometers. Beat that, industry. Oh my God, I'm really impressed with this presentation. Thank you very, very much. I want to continue with the last but not least. The last but not least is something spectacular. This is one of my favorite camera manufacturers worldwide. This is Emberion. And Emberion is here to talk to us about their new product, the new camera system VS20 that works in the visible and the shortwave infrared. And to present this huge achievement, pay attention to this camera. It's quite spectacular. Jiri Hamalainen, thank you very much for being with us today. Thank you for closing the meeting. It's really the last but not least. I think we say the best for the last. Sorry for the other speakers. Jiri, the floor and the attention of everyone goes to Finland, goes to Emberion. It's yours. Jiri, you are muted.
Thanks. Thank you. Thanks. After those words, I feel it's hard to continue when it's so overachieving what you start. So I try to fill your expectations. So hi, I'm Yuri from Emberion, heading sales and marketing, and I want to share as at the end round up the great session we have had today with our novel camera. Let me run a quick video as a warm up. So this shows the Visphere camera we just released at Vision in 1 month ago, which we are now shipping to our customers for evaluation purposes. It's has a spectral range from 400 to 2000 nanometers, and the core is that we have designed the sensor ourselves, manufactured critical parts of the sensor, and built a camera around it. Good applications, for example, sorting for plastic, and also food, but then also very demanding conditions in terms of imaging, meaning, for example, defense. So yeah, that's not that one, but this one, please. So you should now see the camera. So as said, the sensor is a VGA sensor, which we have integrated in a full camera. And you see some of the interiors of the camera left. And about the technology, one brief slide. So we have the core why Emberion exists is the combination of our in-house design IC and the nanomaterials we put on top of it for the sensing the light, the sphere light. So we use quantum dots and some other nanomaterials on top of readout IC that we integrate monolithically, and we get a sensor that covers spectral range from 400 to 2000 nanometers. And its spectral range is wide. I think the key benefit is about what happens above 1700 nanometers, where indium gallium arsenide ends. We have a competitive noise. The dynamic range is good. I'll show you an image so you get an idea why it's so good. We currently have 20 micron pixels, but we can scale them up or down. And I can tell you we offer a very interesting, cost-wise, price-wise interesting alternative to existing sphere cameras. Couple of images. I believe an image lies more than 1,000 words. Oops, not this one. This is our standard sphere demo images. You see the white stuff on the right, on the left, and here on the right you see a sphere image with our camera. Here you see actually the comparison to in-gas camera. Now something is happening with my screen show, don't know what. So look at the sky. This is a standard in-gas camera left, and the right you see an image taken with our camera. They are next to each other out of our office door. So you want to look, for example, at the sky, you see the dynamic range we are reaching with our camera, or look at the balconies, or you might even here see through the car windows. So we offer very interesting imaging capabilities compared to what today's indium gallium arsenide products do. So it's not quite the same what our colloidal quantum dots do. It's different, but we believe it's for many applications, like mentioned, this demanding imaging conditions, or for example, food sorting or plastic sorting applications, it's very interesting alternative. About the technical data, say 400 to 2000 nanometer spectral range today will be extended upwards up to 2500 nanometers in the future. Today we have a VGA array, which is very standard in sphere. In the future, we'll speak about megapixel arrays. Today's pixel size is 20 micron, scalable in both directions. A very important question many customers ask is, what's the speed of the camera? Today, what we'll offer is 100 frames per second camera, and next spring we'll be offering 400 frames per second camera, which is good. Basically, what you get in sphere today, you will get any faster cameras in sphere area. The dynamic range, you saw the image, the sky, the clouds is very good. We have a global electronic shutter, standard C mount, and then as the last point in this slide is the interface. Today we offer camera link. Next spring we'll offer also JIC-E vision and eventually also USB 3 vision, but JIC-E vision is next on our roadmap. I was checking the questions. Application I mentioned. So today we are offering the cameras for evaluation, selling the cameras for evaluation. So for the timing, we shipped the first cameras to customers for evaluation in June, and now we are taking orders for our December ship and batch. So that's where we are. And very briefly about Emberion, 30 people. Cambridge, UK, and Finland. In Cambridge, we do the nanomaterial development, the sensor, the photosensitive material development on top of IC. You see bottom right, our glove boxes in Cambridge. In Espoo, in Finland, we do electronics, IC design, testing both of the sensor as well as the full cameras. So camera part and electronics part happens in Espoo, but we work very closely in two locations. So knowing that we are slightly already over time, and I hope there are good questions, I perhaps conclude it here and hand over back to Jose, please.
Thank you very much, Judy, for a great presentation. And I am very impressed with that dynamic range, really impressed with that dynamic range. 750 EPIC members watching this. What can you do for them? What can they do for you? The EPIC question.
I think I already told what we can do. So we offer pretty unique spectral sensitivity range up to 2000. So it's really what happens above 1700, where you have really challenges of finding a good alternative today, even with the money. Now, what others can do us is really the interesting part. I feel this is an ecosystem. It's not only about a camera when you go above 1700 nanometers. You need lenses, you need light sources, you need filters. And today what we feel is that it's a bit chicken and egg problem, as there hasn't been any reasonable way of seeing above 1700. Our customers ask for it, for example, plastic sorting, but the market is requiring commercial or lacking commercial solutions for these light sources, filtering, lenses. Lenses are coming there, it's great. There are a number of lenses that work well. Light sources, I think, are not there yet. There could be much more filters for between 1700 and 2000 nanometers. So looking forward, commercial solutions there that we can test and recommend them to our customers for off-the-shelf products. So really looking for that one from the other 700 plus EPIC members.
Thank you very much. The first question in the room comes from Switzerland, from MPS Micro Systems. Eugen, what's on your mind?
The question is, you mentioned you have some lenses inside, and are they also, do you have some mechanics inside? Are they movable? Is it kind of a zoom functions, or is it everything static? And
you mean the camera?
Inside, yes, the camera.
So it's a monochromatic. I'm not 100% sure if I got the question right. So you're asking if the interiors of the camera can be moved, or
if you have some movable lenses inside, for instance, for I'm not an optics expert. Maybe you mentioned something how you do it differently, but usually, or what we do for our customers sometimes is just move the lenses for zoom or focus function in the camera inside, for instance.
Okay, yeah, we are not, of course, we have a C mount, so we use commercial lenses off the shelf and test and recommend to our customers. So our camera does not have a lens, it has the sensor and anything behind it, but it's a standard C mount where you click on a standard lens from Kova, Edmund Optics.
Okay. And it would stay on the same place, right? So it's not movable inside, right?
It's not movable, yeah. It's
not motorized. Okay.
Yeah, not motorized. The question is, will there be for surveillance? We have heard from customers at DSCI, meaning the defense sector, requests for motorized lenses in Sphere. So there we see actually an area where there is need for improvement, a kind of a heavy-duty, long-range lens for defense surveillance, for example, on the sea, where you would have it motorized, but haven't seen that on the market yet.
Yeah, maybe we could have a cooperation and develop something together.
Certainly, that's why I'm here. That's why I'm looking for. I was so much looking for Jose's epic question.
The next question in the room comes all the way from Padua, from Dynamic Optics. Stefano, what's on your mind?
For the presentation, that was beautiful, and I'm sure you received a lot of questions about the comparison with InGaAs camera. And again, I mean that. So we use InGaAs cameras for waveform sensors. So we are often working in low light conditions. So I'm interested about comparison in terms of accuracy and signal to noise ratio. Can you tell a bit about that?
Yeah, excellent question. Today we are camera, if you're really in extreme low light condition, I have to say that the evaluation cameras are not yet quite on the same level if you take the best InGaAs. So it's really what spectral range you are looking at. So we have a wide spectral range, and especially the advantage is that if you need to see around 1700, InGaAs is not working there, or you have to go for extended.
Sorry, the main wavelength is 1550 nanometers.
For that one, the current camera is not, if you take the good quality InGaAs camera, we are not in the signal to noise ratio on the same level. There will be further developments with our future products, but perhaps the best way is to test it and see if that meets your requirements.
Yeah, we will. And what about the frame rate? Does it scale up if you reduce the area of interest, or does it still remain 100 Hz?
So the current version, as said, works up to 100. We have specified it up to 100 Hz. The IC actually is specified up to 100 Hz. But next spring, there will be a new version of the IC and camera that will go up to 400 Hz. So it's our IC that we have in the design limited it because of the power consumption for the first version. As said, we are about to do a tape out for the next IC.
What is really unmatched is the dynamic range. It's super impressive. I'm quite impressed with this. Stefano from Dynamic Optics, let's make a deal. I'm gonna ask Giri to ship one of the cameras to Padova. When you receive it, take a picture of you testing that, and I will promote it to the entire Epic industry. And if you want, and actually we'll go to Padova and take a picture with the Emberion camera at Dynamic Optics. Any excuse is great to go to Italy. With this, I would like to thank all the fantastic speakers we had today. I really think that we saved one of the best for the last. I am really impressed with this camera. All I want to say is that stay epic, stay healthy, and start traveling again. Photonics is really, truly fantastic. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the Epic production crew and all sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being epic. Thank you for being epic, everyone. What a great session today. Really, really loved it. Now is when I say the following. If you have to go because you want to pick up the children, because you want to cook dinner,